Welcome. This is the final day of our technical presentations. During this first session too, you might know that Rod Mertz is also our lead in Product of the Year, and he will be announcing the Product of the Year, who won the Product of the Year in the first session. So if you're sitting in this hall, you'll be the one that knows, and when you go down, you can always go directly to where the Product of the Year is and tell them, hey, guess what? You won Product of the Year. Now, we'll try to get hold of them before then. I want to thank you for all of the authors and presenters, because without you, this technical conference doesn't happen. I've heard a lot of good things from a lot of different people, saying how the variety, some of the end users were very happy with some of the variety that they heard. It wasn't all about crude oil or something. I mean, we went all the way from environmental effluent treaters, ramen. It's a full range. So I've been getting a lot of good feedback in that regard from end users. So that's important. And you guys, most of you, are the end users we're talking about. Again, we have 3 papers, and of course this is a bad thing. It says AD Symposium. As most of you know, that's no longer. It's ATC, and I'll get that corrected. There is a monetary reward for first, second, and third, so and there's prestige involved. So the way we do that is the reviewers we have a reviewing team, and that reviewing team goes over each paper and then gives it a score. And then the scores that you give us is 20%, I believe, or 30% of the score on how well the presentation was. So it's critical that we get these from you also. So if you don't have one, Josh has tried to hand them out. Please turn them in, because we will do, after, while you guys are doing the lunch, we'll be working on trying to figure out who won first, second, and third so that we can award that around 2 o'clock. We try to get out of here by 3, okay, because the vendors start breaking down right after lunch, and we come back up here to finish and do the awards and so on and so forth. We want to do, if my phone rings, I'm sorry, I didn't turn my phone off, but while I'm talking about that, how about turning your phone off or going back to vibration? I hope mine doesn't go off just in case, because I'd be a bad penny, wouldn't I? We want you to fill out the evaluation sheets, and if you could drop those off to either Josh or Paul sitting in the back, would really be a help. Please, no commercialism. We try to keep that out of the papers. You're supposed to be giving a technical and not a commercial. And questions and discussions afterward are very much appreciated. And I know that from the people who are actually giving the presentations, really like that interaction. I want to thank you, and I hope you enjoy yourself. I'm going to turn this over to our facilitator for the first session. And if you have any issues or anything like that, come see me down at the registration desk, and I'll try to help in any way I can. Thank you.
Thank you, Wes. First of all, Product of the Year. The big drum roll, please. It'll be JP3 measurement with their XSPCT NIR analyzer. So that is this year's Product of the Year. Give them a round of applause. And, if we could have our first speaker come up, Fabiano. So Fabiano de Malas is the Global Business Development Manager at AVL Analytical Technologies, where he drives strategic growth initiatives for the newly established Process and Environment segment. With more than 2 decades of international experience in the analytical instrumentation and environmental engineering, He has held senior leadership roles in industry-leading companies including ABB, Bartek, and Mettler Toledo. A recognized specialist in infrared spectroscopy for emissions monitoring, Fabiano has led global marketing, product development, and commercialization efforts for advanced IR sensing technologies. He earned his PhD in analytical chemistry from TU Vienna and conducted postdoctoral research at the Georgia Institute of Technology in Atlanta in 2002. Passionate about innovation, Fabiano focuses on delivering solutions that address emerging challenges in emission monitoring and industrial measurement, and sustainable process technologies. Thank you, Fabiano.
Thank you. So, can you hear me? Yes, okay. Hey, good morning, everyone. So, my name is Fabiano, and I work for AVL Analytical Technologies. I'm going to give you an overview today about Fenceline monitoring. There has been already a couple of presentations this week, so I'm trying to go to add some added value today on Fenceline monitoring by describing a bit better what we can do with FTIR, what we have done. I'm going to present you some data that we have achieved quite recently in Germany and in some field tests. All right, so if I press the red button, I go back and the green goes. Let's see, oh, it works, fantastic. All right, so the targets today for me is to give you an overview about regulatory context and give you then an overview about why Fenceline monitoring is important, especially ethylene oxide. And then, as I said, I'm going to give you a quick overview about FTIR, infrared spectroscopy, and of course, the results we have achieved by deploying the AVL FTIR. So my main goal is just to, how can I say, to build trust in FTIR. All right, so those are the 4 points so that we're going through. So what is MACT and why it matters for ETO? So MACT regulates hazardous air pollutants, so HAPs, from organic, chemical, and polymer facilities in the US. We don't have this in Europe. I'm actually based in Germany. We do not use ethylene oxide. This is really, I would say, a North American topic, but definitely very interesting. So ethylene oxide offers some risks, and we're going to go through that. It's actually a toxic substance, as probably everybody knows. And for that, the new regulations mandate Fenceline monitoring to assess oxide impact and enhance community health accountability. All right, so I think those are the main points to be understood why how MACT is important and why ethylene oxide is relevant. So now let's go a little bit more into detail about the regulatory framework. There might be perhaps in the room a couple of people that are very familiar with EPA regulations, much more than I am. So please apologize for the very synthetic overview I'm going to give you here. There has been a training on Monday, which I have attended, which was fantastic about regulations, and I would definitely refer to these guys in case you want to know more about EPA regulations for flare monitoring and Fenceline monitoring. Now, cutting a long story short, the EPA's 2024 HON rules, also known as 40 CFR Part 63, Subpart H, address emissions of HAPs in the chemical sector and polymer manufacturing industry. And there are 6 substances which are targeted. Those are, I read this on my slide, so chloroprene, benzene, 1,3-butadiene, vinyl chloride, ethylene dichloride, and last but not least, ethylene oxide. All right, so and the deadline for Fenceline monitoring on ethylene oxide is actually in a few months, is 15th of July, 2026, even though it's been postponed to July 2027. The reference method is the EPA method 327, which is essentially working with summer canisters. We're talking about 8 canisters evenly spaced in the facility perimeter, and the action level is 100 ppb if we consider these on an 8 hours time weighted average. Okay, so EPA refer to this offline method, so the EPA method 327, however, encourage every end user to go with real-time monitoring technologies, and that's why I'd like to go on with a few slides. So we're going now towards a bit more real-time or continuous monitoring technologies. Before we do that, I thought it might be interesting to have an overview on what HAPs are. So HAPs, as I say, is just an acronym which stands for hazardous air pollutants, and they are essentially substances which are not really very friendly to human beings. Common examples, I took the freedom to report here a couple of examples because one could think it's only gases, but it's not. So there are VOCs, which of course are gases, so volatile organic compounds. Everybody knows benzene, toluene, and xylenes. Ethylene oxide is gonna be the topic today, but also metals like arsenic or lead or chromium are also reported as HAPs. All right, so sources of HAPs are usually from stack are essentially 2, stacks and everything which is non-stack. So what is non-stack is called fugitive emissions, and in simple words are leaks or leakages from within the facility. So what is Fenceline monitoring? Exactly, for those who are not maybe familiar to the topic, I thought I always like to give a definition on things, and for me, well, actually for the community, Fenceline monitoring is actually measurements of HAPs along facilities property lines, so what is called also perimeter of fence line. And the goal is to detect and control fugitive emissions from those sources like refineries or petrochemical or chemical plants, as I said before. Why is important? There are essentially 4 reasons why Fenceline monitoring is important. The number one is because we want to identify where unintended sources of ethylene oxide or HAPs are. This can be, for example, storage tanks. Number 2 is because there is a regulation, so we have to do it. Number 3 is to be transparent against the community. I think Fenceline monitoring provides data that can be, it shouldn't be, but can be transferred or made available to communities to offer transparency, right? And number 4, Fenceline monitor can be used to identify very much in detail the hotspot where the pollutant concentration are highest, okay? So it really goes into very detail here. And there are ways how we could do this. Now, before we go to too much in details on FTIR, I thought let's take a close look at what is ethylene oxide monitoring and the use cases. Okay, so Fenceline is one of them. It's not the only one. So while ethylene oxide is monitored and measured, as I said already a couple of times, stack monitoring is the other one. And the definition is continuous. So what is stack monitoring? Is continuous measuring or monitoring of emitted ethylene oxide gases from the stacks, okay, which are different from fugitive emissions. These comply with SEM regulations, essentially the PS, so product specification 19. Number 3, we have working areas. So ethylene oxide can be present in working areas like probably everybody knows, or maybe not. But anyway, so if I'm working in a sterilization plant, it is likely that ethylene oxide is present in my working environment. So for safety, okay, ethylene oxide should be measured. And then spot check. So once I know there is an ethylene oxide, I might want to identify a specific area and check what the concentration is. All right, so I'm going to go very quick here. The alternative methods is where we're going to, where we're hiding to. Method 327 is good, however, is offline and offers several disadvantages. It does not identify where emissions come from. Okay, I assume I have a canister somewhere in the field, okay, which is accumulating ethylene oxide over 24 hours. I cannot really tell you whether this is, I mean, we have an ethylene oxide leaks 5 minutes ago or maybe 23 hours ago. It's not clear. We also don't know exactly where this ethylene oxide leaks is coming from. So it does not resolve spatial gaps. So this is why continuous and real-time monitoring is probably a good option. It's not a must, but it's a good option. So among the several technologies, and there are multiple ways how you could measure ethylene oxide, I mean analytical technologies, I took the freedom here to report what I know best. So cavity ring down, spectroscopy, tunable diode, laser absorption spectroscopy, FTIR, and advanced FTIR. I will clarify in a moment what we mean by advanced FTIR. So CRDS, so cavity ring down, is extremely good when it comes to measuring very low concentration as well as TDLS, but for small components. While FTIR look at the broader spectrum, so it can simultaneously measure multiple components, so ethylene oxide as well as other substances. And it works also in a multi-stream combination. Now, let's take a look at why FTIR as well is suitable for MACT application. So first is, as I said, multi-pollutant detection. By looking at the broader spectrum, I can take a look at different components simultaneously. FTIR is deployed as a hot and wet system. For those who are familiar with SEMS or continuous emission monitoring systems, you know that you can either measure dry and cold or hot and wet. So with FTIR, we measure hot and wet, which means we follow the PS, so product specification 19. It's a very highly sensitive technology or technique which comply with EPA regulation, as I just said, and it offers the option to measure multi-stream. So you can have a stream selector, or you can do this optically. So one system can actually be deployed for multiple streams. Now, the methods for ETO monitoring available, once again, I took the freedom here to report what I been found to be current setup and current situation with ethylene oxide monitoring methods. So we have the method 327, as I said multiple times, which is derived from the method TO 1515A, essentially used for ambient air and fugitive emissions, is an offline measurement. It utilizes canister. The canister is brought to the lab. In the lab, there is a GCMS waiting for the analysis. And a couple of hours after the canister is there, you will have the result. Fantastic technique, very precise, very accurate. LOD, the best that you can get. You accumulate a lot of ethylene oxide in the canister, so it's a concentration technique. So we can go well below 0.1 ppb, so fantastic. However, it requires some manual efforts. On the other side, we have online techniques. So the method 320, which can be used for stack emissions as well as for fugitive emissions. It requires the utilization of an FTIR, the typical LOD. If you research a little bit on what other vendors can offer and what I'm going to present you today ranges between 0.5 and 2 ppb, I'm sorry. It's a real-time measurement, it's multi-component, and it's multi-stream. The method 431 is essentially used for sterilizer. It's a GCFID-based PID detector can be used as well. Limit of detection usually ranges in the 200 ppb range. It's very simple, direct, however, might not always be suited if you want to go very down in the ppb level. Now, last but not least, I thought it might be interesting here to report the action level for occupational exposure, which is 100 ppb. Okay. Now, EPA says that the limit of detection should be no more than 20% of the highest range, so being this 20 ppb. So we therefore derive that the maximum allowed LOD for those measurements should be 20 ppb. Now, I promise this is the only commercial slide, but I think it's important to know it. FTIR can be deployed outdoor for real-time as a wall-mounted, for example, a wall-mounted version for outdoor installations, eventually equipped with HVAC, monitor multiple streams, and has a typical measuring cycle less than 15 minutes. You can also use the same bench, optical bench, as a portable device, okay? You just put it in your backpack, go around, and then measure ethylene oxide as a spot check measurement. The 90 seconds is the measuring cycle in this case. All right, so I know there has been a complete training on FTIR or on infrared spectroscopy. So for those who are already very familiar with infrared spectroscopy, you can fall asleep anytime, okay, and resume in a couple of minutes. If you're not familiar with infrared spectroscopy, it might be interesting to know that infrared spectroscopy is a technique which is used for measuring concentrations. The electromagnetic field we're looking at is positioned between 625 and 400 wave numbers, or 16 and 2.5 micrometers, which is a fantastic range if you want to look at vibrational reactions from the molecules, which are giving you a signal and allow you to identify which type of molecules you're looking at. So that's why we're looking into this range. Yes. So I guess everybody in this room might have heard already once in life about the Lambert beer or Beer-Lambert law. You shine light into a sample, and the light passes through. Part of the light is transmitted, part of the light is absorbed. Okay, you can measure with infrared spectroscopy either the absorbed or the transmitted light. In FTIR, we typically take interferograms, so we take 2 interferograms. One is the interferogram of the sample, the other is an interferogram of the zero or the background. We use Fourier transform to deconvolute the signal. So the sample interferogram is turned into a single beam spectra or spectrum, which is the spectrum of the background plus the sample. And the interferogram of the zero is just a background. So if I subtract the background from the background plus sample, I get the sample, which is typically what you will see on any FTIR. Okay, and this absorbance spectrum is always proportional somehow to the concentration of your analyte. That's how we work at AVL, like every vendor in FTIR. It's a very well-known technology. What we have special about our FTIR is the resolution. It's important to have a specific, if you want to go to measure in the low ppb range, to have a very high resolution. So you can understand that if you have a resolution for wave numbers, it might be more difficult to identify and to distinguish peaks, okay? But if your resolution is very tight, okay, like 0.5 wave numbers, then you can go down pretty well. And that's what we have used for this test. So here is the optical setup that we initially done. We have done 2 tests, one in summer and one in winter. The summer one is the one that I haven't reported data here. I'm just telling you we have achieved a quite interesting LOD at 25 degrees Celsius by using an interferometer with a gas cell 5 meters length, optical path length, and with a scan rate of 1 hertz. Okay. Also, the frequency of your scans is important. Then we repeated these measurements in a kind of more complex, advanced setup, which is the one I'm showing you here. So we changed the optics a little bit. So we increased the temperature up to 150 degrees. Our cell can go up to 190. We utilize an MCT detector a bit better than the previous one. So an MCT detector with a high D star, so more sensitive, and measuring between 3,350 wave numbers and 2,850 wave numbers. So exactly where ethylene oxide absorbed. We stabilized the enclosure, thermoelectrically cooled stabilization, which of course helps a lot. Everybody working with FTIR or with infrared spectroscopy knows that temperature is a big parameter or factor that influence the measurement. So the more stable it is, the better it is. And we increased the recording frequency from 1 hertz to 5 hertz. Oh, I'm sorry, maybe, before I go to that slide. So we use nitrogen ethylene oxide. We use one of our GDUs, so the gas divider unit, where you inject nitrogen, you inject ethylene oxide. You can create different blends. We use also an evaporator, a NovaCal, because we wanted to see the interferences of water and methane on these measurements. So this is not yet finished. Actually, it's finished this week, so I haven't the data reported here. But we have this. All right, so we have measured the water interferences as well as the methane interferences. Now, these are the results. We could achieve different steps between 23 ppb and 103 ppb, with some step at 56 ppb. We went up and down, down and up and down, and you can see that the transition, so the reaction time is quite interesting, quite good. The stability, as soon as you reach a signal, the plateau is kept for a while, and quite fast. So we can see that the reaction time is ranging between 60 and 90 seconds. All right, with this slide, I want to show what's the noise, and what's the limit of detection. So we utilize the Allen deviation reading, which is somehow telling us that in order to have a healthy noise, okay, we need to stay in what we call the white noise, okay, until we are on this, in this side of the graph, okay, which is with a bias, with the slope of minus 0.5, we are good, okay? As soon as the noise starts flicking, then it doesn't work anymore. So we need to take exactly that point, which is for us, on the y-axis is the time, and on the x-axis we have the concentration. So we can see that with 90 seconds, we get 0.6 ppb, all right? And if we take this as the noise and we multiply this by 3, we get the LOD. At least that's how we thought we want to define it. So we got an LOD of 1.8 ppb. You remember that I told you the minimum that EPA is asking for is 20 ppb. So if we achieve 1.8 and the requirements is 20, I think we're good with FTIR. All right. So I'm coming to an end, slowly. So the laboratory results are showing that we could measure between 23 ppb and 103 ppb with very fast response time. Okay. Number two, we could determine the noise, and we see that using Allen deviation white noise, we can go up to 90 seconds with a very good noise, which is determining the limit of detection and setting this up to 1.8 ppb at 150 degrees. Thank you. Yeah. So well below regulatory action levels. So the baseline we could see was relatively stable, which I think has been an excellent achievement. Last but not least, I'd like to highlight the benefits of using FTIR for on-MACT Fenceline monitoring. And these are my last comments of the presentation today. So high sensitivity detection. So FTIR can achieve low detection limit, 1.8 ppb for ethylene oxide in lab environment. Multi-component monitoring. FTIR is looking at the broad spectrum, can measure multiple components, benzene, xylenes, vinyl chloride, 1,3-butadiene. Those are all components that could be added. It's compliant, okay? FTIR supports regulatory compliance and operational needs with PS, so with Part Specification 19, and can work in a multi-stream mode. All in all, we believe that with multi-component, multi-stream, compliance to PS19 at 150 degrees and this high sensitivity that we could achieve offers great benefits for the end user, since it can bring the cost down quite a bit. All right, thank you.
Our next presenter is Paweł Kluzinski. Did I get that? Awesome. He's the founder and CEO of AirOptic. He holds a master's in physics and a PhD in tunable laser spectroscopy, with research spanning chemometric methods for gas sensing, optical design, and signal processing. From 2002 to 2010, he worked at Siemens, helping design 3 generations of TDL analyzers. In 2010, he founded AirOptic, where he led the development of the GaAs series and continues to serve as CEO. In his free time, he enjoys traveling and scuba diving. Thank you, Paweł.
Thank you.
And green is forward, red is back.
Okay, great. Okay, good morning, everybody. Thank you very much for the introduction. And so today I will talk about recent development or recent research project that we had together with one of the universities in Poland. And this work was concerning trace moisture detection at high pressures, incorporating a new type of laser device. It was a gallium antimonide VCSEL laser. And I will explain what's the difference between VCSEL laser and DFB laser in a moment. Basically, I'm just presenting the results. It was the most work was done by Bartosz Kamiński, my PhD student, who is carrying out the research. So I will start with the outline. So I will briefly present our multi-laser tunable laser technique. So something I already presented in last ATC sessions. I will continue with trace moisture sensing in LPG, so liquid petroleum gas, in general in hydrocarbon backgrounds, and what are the challenges and what are the obstacles and how we can resolve those. And finally, I will proceed with applications. So extractive analyzer first, so extractive moisture analyzer utilizing this VCSEL laser, ambient pressure that elevated pressures at 7 bar. So for the TDL, reaching 7 bar direct measurement was a challenging task, but we solved it with the VCSEL laser. And finally, something that we are still working on is the in situ TDL analyzer utilizing the array of lasers. So we have a 2x2 array of VCSEL lasers. I will show you how it looks like. And finally, I will conclude the talk. So to begin with, I think you are very much familiar with absorption spectroscopy and tunable laser spectroscopy. I will just basically go through briefly, what's the principle of operation and what we have done differently with the multi-laser technique. So you have a transmitter and receiver units on both sides or opposite side of the process. So if it's in situ system, you have a transmitter and receiver unit mounted on opposite sides of the stack. For extractive system, you have a cell, gas cell in between. It can be multi-pass cell, it can be a single-pass cell, you name it, depending on the process and application. But the principle is the same. You are looking at absorption signal. In our case, we use wavelength modulation to enhance signal-to-noise ratio. And we have also developed a way how to multiplex different sources together in one unit. And this has been done optically and electronically, how to combine those lasers. The rest is basically the same as any other TDL system. So you need a detector and receiving unit. And there is a reference cell. So the yellow unit here is the reference cell used for line locking and auto-calibration purposes. And it's constantly there on the receiver unit, regardless if it's extractive system or in situ system. And regarding the lasers, so we can use anything from 760 nanometers up to 6,000 nanometers, so utilizing, say, near-infrared and mid-infrared lasers. So we basically developed a broadband optical combiner in order to do this. And we also can combine telecom-grade lasers like this indium phosphide DFB, gallium antimonide DFB. So these are the kind of classical diode lasers, together with interband cascade lasers, so the quantum structures spanning from 3,000 nanometers to 6,000 nanometers. So this is basically, this combination can be done arbitrarily. So you can, depending on your, we of course have standard application, but we can also make a combination of gases that you want to measure. So regarding moisture itself, so moisture measurement is by far one of the most difficult components to measure, maybe except H2S. And there are several tasks that have to be resolved before making a good low-level moisture analyzer. And I won't go into very much details. The work was presented 2 years ago, so 0 to 1 ppm moisture detection system. I will just mention a few key points and then go to the new research. So you need a very good base sensitivity, so 10 to the minus 6 relative absorbance. So this is a key, that you need to have a base sensitivity in order to make a low detection limit. Then the right selection of wavelengths. So for moisture, there are several choices in the mid-infrared, near-infrared, but you have to do it carefully depending on your application, because if you measure moisture in hydrogen, it's very easy because there is no interference, but if you measure it in very complex hydrocarbon mixture, it's very, very complex, yes? So you have to do something about it. First, choose the right wavelength, and then do also some trick with pressure lowering. That's what we did. And of course, all the mechanical elements and coatings need to be in place, so silicon earth and just to get the very fast response time. And last but not least, customers also ask, how do we validate moisture analyzers? So finally, we have gone through many different ways of calibrating. So you have a surrogate gas concept that it could be utilized, but we also use the permeation tube devices that are possible to use in the field. Okay, so when you use the mid-infrared laser, the trick to get down to the low detection limit without making a differential spectroscopy is to lower the pressure. That's something that is used in our analyzer. And the effect is straightforward. By lowering the pressure, you minimize the collision broadening, and then your line width is getting narrower by 10 times. Yeah? So basically, you can avoid any hydrocarbon interferences this way, and you don't have to make any active background corrections, yes, or you don't need to use any scrubbers. And this was working very well and very well proven in the field already for several years. But the drawback is, of course, that the system has a pump inside, yes, and then you need to lower the pressure in your sample and conditioning system. So ideally, we're asking us a question, okay, can we measure moisture without doing this pressure lowering trick? And then, of course, the answer was not easy in the beginning, but then we started to look, what can we do? So if we could somehow increase the tunability of the laser to cover broader spectra, that's what Fabiano mentioned with FTIR. That's if you can scan longer wavelength, then of course, you can do a better math and you can cover, larger spectral range, yes, and you have a better measurement. So we were thinking to use not a standard DFB, so distributed feedback laser, but a VCSEL laser, vertical cavity surface emitting laser, and use it at the wavelength in a very short near-infrared, so 900 nanometers, and also cover the large wavelength range. And this was the key how to do it. And the rest is basically the same. Moisture analyzer parts can be utilized from the old system that are basically commercially available today. So what is the VCSEL structure? I assume this was already introduced in some of the papers on spectroscopy. So vertical cavity surface emission laser is a different kind of laser that emits light along with the current. So it emits a light from top to the bottom to the top of the layers, active layers. So it means that you can already emit some light on the wafer structure before processing. So the advantage is that you are eliminating any facet processing, and you can grow mirrors with epitaxy. So it's potentially, this is a very low cost process, and that's why you use VCSEL laser for proximity sensors, for automotive, industry, and so on. The same idea, okay, can we do it for spectroscopy? And that was the whole idea about this research project. So we developed a special laser for this application, especially for moisture, with a very special structure. It was based on the quantum dots active layer, and you use a distributed bulk reflector as a bottom reflector. That's a standard stuff for VCSEL. But the new thing was also that the top mirror was made by lithography. It was a nanograting. And by changing the structure of the nanograting, we could select the emission wavelength. So we could make, say, exactly the emission wavelength of our choice, and then use it for moisture measurement. So in general, this was the assumption and idea of the project. And then the laser was made. That was also made in collaboration with our German colleagues in Berlin. And this is how it looked like basically after processing. So the light emitted from this device was at 930 nanometers, where we have a nice moisture spectrum, free of hydrocarbon background. And so as you see on the top left picture, the bottom contacts where you apply a current are there. There's a ring, and there's the same on the cathode on the upper structure. So the current goes through, and then you're actually creating the light along the current. And then so very simple method. Then you have some set of apertures to control your perpendicular modes. So in the end of the day, when you do it right, the emission beam is very nice. So very nice divergence, around 15 degrees divergent beam, yeah, very nice profile. And the only drawback is, of course, VCSEL is not high power device. Yeah? We are talking about low milliwatts range, but you don't need more for spectroscopy, especially for the extractive systems. And just as a different example, we already have used VCSELs for the electrolyzer measurement for oxygen. So prior to this moisture measurement, we already have done oxygen sensor for hydrogen application in the range of 0 to 35 bar G. That's by far our record in how far we can go with pressure with in situ measurement. Yeah. And this was deployed on one of the small size electrolyzers with good results. And this was possible because VCSEL that we used had a very high tunability. The range between typical values are between 100 and 300 gigahertz per milliamp. And compared to the standard lasers of DFB type, it's only 1 gigahertz per milliamp. So you can see that you can tune much more the VCSEL lasers and get better spectral coverage. But of course, VCSEL does not have the same current range. So you are basically maybe a factor of 10 better than the standard DFB. But it was one of the good examples of using VCSEL for spectroscopy. And the rest basically is the standard extractive system. So we put it in our standard enclosure. We have this system also here, not for moisture, but similar type for CO. There is a multipass cell of Harriot type. So very, very stable structure, 7.6 meter path length. And the only thing basically we change is the laser, because the detector is a standard silicon detector. And so these are the results, how it looked like in air and in LPG. So you see the line, the moisture line with the LPG matrix is free of interferences. It's only slightly broadened. Yeah, this was expected. And the next step was, okay, if we do not have any background interference, then we can increase the pressure because we can tune more. And that was the trick that we did. And so finally, we could reach 7 bar pressure when we could still measure some moisture. And these are the results. So we use our permeation tube device it was calibrated to the NIST traceable standard by Kintec moisture generator. So standard testing procedure. Response time, couple of minutes, how you actually do the step response. So the same as for other moisture analyzer. This is more related to the the material choice and the flow rate rather than response time of the laser itself, because the laser is instantaneous. So we have sub-second detection T90 times. Yeah. So looks quite good with this laser. And now we have done also some drift checks. And so first, zero gas sample, that's kind of our benchmark. We put the system in the climate chamber, and we also see what is the response to the zero gas. And then we also performed the Allan deviation plot that Fabiano mentioned. This is a very good way how to test stability of the analyzers. Difference with FTIR, for example, of the laser is that for TDL, we always observe this rise on an Allan plot curve due to the drift. And so the sweet spot is not always, at the maximum integration time is somehow earlier. But the results, anyway, were quite impressive for this wavelength. So 0.06 ppm at 2,000 seconds response time. Okay, if you want to wait that long, but normally, it's sub-ppm detection, which should be sufficient for, a lot of moisture measurements. Yeah. And then the higher pressure, the results were a bit worse, also expected, because we observe higher drift on the value. And this is due to the optical noise, because we have to modulate laser frequency slightly higher, slightly 7 times higher than the atmospheric pressure, which means we see some residual amplitude modulation noise plus optical ethanol noise. So, but that's kind of first results we got. Still sub-ppm detection, still sufficient for most of the moisture measurements, in LPG. Okay, and then now the next step was to not only use one laser, but use the same structure on the array. Yeah, so basically you have the same TO5 can as you see on the picture, and then there are 4 lasers mounted close to each other on 1 by 1 millimeter area. And you can activate those independently from each other. And then, the structure was done in the following way, that the central emission wavelength for each chip was different. Yeah? So we could make a kind of semi-continuous tuning by tuning between those lasers, yes? So we could cover much broader area. And that's the spectral graph, yeah? So you see we span from 936 nanometers up to 940 nanometers with 3 lasers together, yeah? So we could stitch these measurements using 3 VCSELs. Why 3, why not 4? Because one of them, unfortunately, has died, and so we were still only using 3, but still we could cover a wide area. And you see all the moisture lines in this range. And you can apply a chemometric model to all of them, so you increase your signal-to-noise performance and, of course, the accuracy of the measurement. So that looks quite promising. And so now we have set up a in situ model. So we put this array into our standard in situ system, and then using still standard optics. And it seems like it can also be applied for in situ measurement. And the challenge here is, of course, that the chips are not exactly in the right position regarding optical axis. Yeah? So you have some deviations from the ideal beam shape when you collimate. But if you look at this picture, that's the cross sections of the collimated beam after 5-meter path. So it's, assuming you have 5-meter path, they still look very good because the distance from the optical axis here is between minus 10 and 10 millimeters. So the beam is still around, the normal size, nominal size of the 16 millimeters what we have for our crosstalk. So it is definitely collected by the receiver lens, which is 40 millimeter, and falling in the right place on the detector. So that looks very promising. I don't have more results yet available for how it performs with moisture, but at least optically, it looks very good. So basically, that was all I had today. So to conclude, yes, so our multi-laser technology has been successfully proven for trace moisture using a mid-infrared devices, but now we basically would like to remove this necessity to have this system to lower the pressure. We want to measure in situ up to 7 bar, either with extractive system or the crosstalk system. And the key thing is that there is no spectral interference from hydrocarbons at this wavelength, so which is a beautiful thing. We have to challenge this problem in the mid-infrared. And so potentially this could be a low cost system, a low maintenance system. So we are looking forward to see further development in this area. So thank you very much for the attention. I am happy to take questions.
Thank you, Pavel. Do we have any questions from the audience? Yes.
May I ask what's in the reference cell or gas?
Well, the reference cell depends really on what you have for the application, but for the typical moisture application, you can use either some hydrocarbons or CO2.
But for this one?
For this one, actually, this is you have a moisture signal as well. You have a moisture cell.
Oh.
So it's water vapor, but there is a special condition there.
Yeah.
It's a special pressure. Yes, so we use the same gas in this case, yeah.
So the reference cell pressure is the same as your process? 7
No,
bar?
it's not the same. That's a trick. You don't want to have it at the same pressure, because otherwise you have problem to distinguish between the reference gas and the process gas.
Also, you intentionally make the pressure different?
Of course. Yeah.
Great, thank you. What's the path length of your cell?
7.6 meters.
Okay, good, thank you.
You're welcome.
Thank you. Anyone else? No? All right, thank you, Pavel. Our next presenter, Michael Frank, is a product manager for gas chromatography products at Valmet with a background in chemical engineering from the University of Karlsruhe? Karlsruhe, okay. Where is that? That is in Germany. Ah, okay, okay. Michael brings a deep expertise in gas chromatography with more than 2 decades at Valmet, starting as a project engineer designing analytical systems. He was spanning different roles in engineering and sales. He joined his role as product manager in 2018. Amongst traveling and hiking around the globe, he enjoys translating complex technology into practical solutions and is passionate about collaborating across teams to deliver customer value. I'll give you when you've got 5 minutes left.
Okay, thanks a lot. So thank you for the introduction, and let's see how that goes. So welcome to my presentation on intrinsically safety in process instrumentation. So the motivation of the presentation is basically to give you a better understanding of intrinsically safety, how it is used, what are key features of intrinsically safety, and also highlighting the practical uses for users and operators, and giving some practical examples at the end of my presentation. So process industry brings together, especially in petrochemical and oil and gas, brings together a lot of different technologies. One of them, for sure, is the need for sophisticated measurements, instrumentation, and analyzer systems, providing the necessary information to operate and optimize processes. All the more in a very demanding environment, as flammable materials like dusts, vapors, gases, and liquids are present in the environment of those measurements. Actually, the protection of explosion in these environments specifically pose a broad field of different technologies and techniques, usually summarized as protection methods. So intrinsically safety is one of these techniques and is widely used in process instrumentation and automation. And I just want to highlight the advantages here. So protection methods usually focus on the avoidance of ignition as possible or hazardous materials like flammable materials are present in the environment together with the ambient air. The basic functionality of the protection methods is again the avoidance of ignition, mainly focusing on the reduction, containment, or avoidance of those ignitions. Now, intrinsically safety specifically focuses on the avoidance of these ignition sources, mainly focusing on the lowering the applied energy to levels where hot surfaces or sparks are no longer possible. So how is this achieved? Usually the standard defines energy limits with limiting curves, like for example what you see here. So basically defined energy levels by the material characteristics of the flammable ignition energy that is required. Different categories and groups are achieved with different levels of energy. All the more, providing safe and reliable products or devices, intrinsically safety also takes into account a broad assessment of faults under fault conditions and design faults, and I will highlight that a little bit later. So intrinsically safety and the advantages is broadly used in process industries, mainly for instrumentation, like low power applications, transmitters, or positioner valves, which kind of gives the ability to install those components in a decentralized, on-the-spot applications, well, without the requirement to really implement those and integrate those with the high integration costs for excessive or let's say elaborate installations. But also complex analyzer systems profit from the intrinsically safety advantages, as methods can be simplified, installation and integration is highly simplified, and also maintenance is reduced to a point where it's highly advantageous for those components. So overall, giving advantages in regards that over the life cycle of such instrumentations, intrinsically safety can have a huge impact on the costs of operating these systems. Overall, intrinsically safety providing safe devices in hazardous areas is really an advantageous technology in this field of operating instruments and analyzers. So how is intrinsically safety applied? How is it used? Basically, this is defined by the standards and the regulations. And this comes from basically starts with the hazardous area categorization. So standards define how these areas are defined. For example, the National Electrical Conduct is the NEC defines this with a class division and group classification and a probability of faults and fault and non-fault operation. For example, also the IEC, the International Electrical Commission, is defining this with an approach of the probability and the possibility of available flammable materials, taking into account then equipment protection levels in order to categorize different zones. Both or all hazardous area classification techniques or standards take into account the probability and characteristic of flammable materials in the presence of ambient air and take into account the protection methods that are then applied in these areas in order to provide equipments and classification of equipments that can be used in these areas. So the standardization of these protection methods define then how equipment is manufactured and designed in order that they can be used accordingly in the hazardous areas. So while operators define the hazardous areas, standards then define the technologies and techniques how to design the devices to be used in those areas. And finally, manufacturers can then apply those technologies as described in the standards to their equipment so that both worlds then come together. First of all, the hazardous area classification as well as the equipment design, so that via the classification and the certification of the equipment, you can create a safe environment. As of that, intrinsically safety is defined by the IEC standard 679-11, and then that is the general global definition of how the design is supposed to be. And then it is adapted to the regional regulations via the national organizations. Again, for North America, this is NEC via Article 504, or for IECX and ATEX, it's another IEC standard 679-14. So while the global standard defines the design of the components, and the national organizations make then the adaptations to the regulations and requirements of the local hazardous area protections, this makes this technology really a very, very nice and feasible technology for equipment manufacturers, as you can design then a device for a global use, while national certification organizations take then into account the national regulations and via certifying this, usually only takes specific nodes and specific commands into account how to operate these systems then in the national environment of the regulations. Yeah? So intrinsically safety, again, as it is defined in IEC 679-11, defines certain components of the intrinsically safe components. Yeah? So first of all, you have the intrinsically safe apparatus, or the IS device, which is installed in the hazardous areas, and per definition, the definition of the standard, is a device that does not pose an ignition risk. It's intrinsically safe, so to say, in regards that it cannot create any risk situation. Additionally, the associated apparatus, or the IS barrier, is defined by the standard, and this is kind of a device that is powering the IS apparatus in the hazardous area in a way that the energy is limited limited to supply the energy, yeah? In a way that that you can, for example, imagine that like an overflow or release valve, that all excessive energy is drained and only a limited energy is provided to the device. And this is achieved with electrical components, for example, a xenodiode. Yeah? So bringing together the IS device as well as the IS barrier and connecting them with a wire, this creates then the intrinsically safe circuit, and that can be then categorized and applied in hazardous areas. So in order to apply then the hazardous area classification, different levels of protection are defined. So for NEC and class and division categorization, intrinsically safety actually can be used in division 1 and zone environments. While for the ICX and ATEX categorization, there is an evaluation and assessment of possible faults under onerous conditions. So that means that it's under maximum conditions in regards to the energy that is provided to the device, as well as maximum ambient conditions, like, for example, ambient temperature. So a large evaluation or an excessive evaluation of faults is done in this standard, and there is a definition of possible faults, countable faults, non-countable faults, as well as design faults and obvious faults here. Actually, this fault assessment is, from my point of view, the differentiator of other protection methods, as actually this standard takes into account that faults can happen, faults are possible, and taking this into account in the device design actually makes and provides very reliable and safe devices that can be used then in hazardous areas. So the standard actually, additionally to the energy limitation, also provides quite a very detailed design specifications on how intrinsically safety systems and devices are designed. So for example, here you see two examples here for creeping distances or for distances of electrical components on printed circuit boards. And it's very detailed in the description of these components. Yeah. The standard also defines specifications or specifies additional protection methods like molding, like covering, like specific distances that have to be kept, also taking into account then safety factors, additional safety factors, all the more than in order to provide then this safe device, this intrinsically safety, in order to establish the intrinsically safety. And you can imagine that designing such systems is quite, let's say, difficult, or it takes a lot of efforts as all the assessments during design have to be provided. However, at the very end, what you get is a very safe and reliable device in itself. as the complexity actually is integrated into the device via taking into account all these design specifications. So finally, now that you have your device, your intrinsically safe device, and what is required in order to operate this, per definition of the standard, that's a document, a device specification, and a document that needs to be provided that kind of puts all system components together. So here you see an example of such a document. First of all, you see the block diagram of the components, so the intrinsically safe device as well as the safe barrier and the wires that are connecting both devices. All the important information needs to be given in the document, like the manufacturer, part number, description of the device, also the description of the protection level, conditions of use like ambient temperature, surface temperature, as well as the electrical parameters need to be given for both components, or including also the wire. The electrical parameters are then assessed and proven to prove that the intrinsically safe electrical limitation is provided with the design, and that is also then given in the documentation as the assessment here. Additionally, then also grounding points, bonding points, power supply, and all conditions of the systems are given, as well as specific notes how the intrinsically safe circuit is used and applied. And finally, the document gets a number to identify the circuit. So given all that, this is kind of the justification that the intrinsically safe circuit is established and can be used in the field. So after all that standardization, fault assessment, description, documentation, I would like to highlight really the advantages of intrinsically safety. And given that you have a component that is not considered to be an ignition source in itself, has many advantages in the application of those components and devices. For example, you have low costs for installation, as they can simply be installed in the field. It also, the maintenance operations and procedures can, due to the simplicity of the system, reduced. For example, you can also do a live maintenance. You do not have to power down the systems. And for sure, you have a device that does not compromise at all the safety of your plant and of your plant operations, as again, the design is considered to be intrinsically safe. And to highlight this, just a few examples. For example, here you see the integration of two flow meters on a standard sample system. You see that the connection does not require specific or excessive components here. Actually, you can see the components as general purpose devices, which can be installed in hazardous area easily. Yeah. And again, it makes or provides then a simple way how to integrate on-the-spot devices without the need for excessive protection. Another advantage of intrinsically safe devices is that it usually ends up in a very robust and complete compact module. So for example, here you see intrinsically safe electronic pressure controller. It's a very compact design. The cable is fixed to the component itself and ends up in a plug that can be connected then to the intrinsically safe barrier. So again, this shows that very simple devices finally result out of the intrinsically safe design. And actually, that also then simplifies the maintenance, as these devices, per definition, cannot be repaired in the field. Actually, repair is very limited and can only be done by the manufacturer himself. Usually, those components cannot be disassembled and not be repaired in the field, which again is one of the key characteristics. Yeah? So that way, the only way how to repair such a system is mainly to replace it. And you can now say, okay, that makes higher costs in the maintenance, but on the other side, you can keep the maintenance time and downtime of the system very low. And actually, what is the main advantage here is that under any condition, you are compromising the safety of the system, as you just exchange the component and it is safe as in the design. Yeah? And finally, in regards to the life maintenance, here you see an intrinsically safe thermal conductivity detector for a gas chromatograph. You can, as faults are considered in the design, do maintenance under live conditions. So you do not have to shut down or de-energize the equipment, and you can do the exchange of components here while it is still powered. This might look a little bit over excessive, and then it's maybe not necessarily required, but I think that this really points out that this fault assessment is really one of the big advantages of this technology. As you can, for example, imagine that cutting off a cable does not pose any risk, as sparks cannot be created. As well as, for example, if you do a maintenance work and you kind of forget to connect the cables, this does not pose any risk to the equipment. And again, the system safety is not compromised at all. Yeah? So in conclusion, I hope you have now a better understanding on intrinsically safety, how it is used, what are the key characteristics and advantages of intrinsically safety. And again, the advantage in regards of process instrumentation and automation, given that you have overall very reliable, very safe devices that you can use in the field and practically install them in any hazardous area. So thank you for your attention, and do you have any questions?
Do we have any questions for Michael? Oh, come on. Someone's got to have a question. Okay, I have a question.
Okay.
Cost of manufacturing IS versus the traditional NEC. Based on your presentation, it would seem like there's a bit more to the engineering phase and that sort of thing. Is that true?
Yes, for sure. Again, the design is very complex in itself. Yeah, for sure that confirms then with higher costs of the devices. Yeah, so that usually is coming along with that. Also in regards to R&D and developing those systems, that is also kind of very challenging at that point. Yeah, for sure. Yeah.
Fair. The other question that comes to mind is, I'm assuming that this still doesn't, you would still have to, obey hot work permits and all that sort of stuff in a refinery. That doesn't absolve you from any responsibility for those types of procedures, right?
For sure. I mean, operator procedures need to be still in place, and in order to sustain the safety of the system during maintenance, for sure that is a main operator requirement, how you do this and what processes you apply. However, again, with the intrinsically safe devices, those processes can be simplified, can be reduced, and also that is an advantage of the usage of intrinsically safe devices. As for example, you do not have to consider certain conditions, and also specifically in regards to confirming that safety is still maintained after the maintenance. That is not a requirement, for example, when you use intrinsically safe devices. Yeah.
All right, any other questions other than my own? All right, thank you very much, Michael.
Thanks. Thank you.